Okay, so now we're going to do an example where we find the potential function of a vector field. So this is really how we want to think about it, where we start with a given vector field, and then for that vector field we find this potential V. So I'm telling you this vector field admits a potential function. Again, not every vector field will have this property, and it's not clear, for now it's like a black box. How can you determine ahead of time whether or not a vector field has a potential function? That will require discussing a bit more tools, namely Stokes' theorem and Green's theorem. But for now, it's just a fact that this vector field admits a potential function. Remember that that means in practice that you can write f as a gradient of some scalar field, which we call V. And the point of finding V is that once you know V, the work will be very easy to compute. So in this example, I'm taking the particle from the position 1, 1, 1 to 2, 2, 2, and I'm going to take it along this weird spiral, right? And so if you wanted to compute the work in the ordinary way, this would be very difficult because you would need to find like an actual formula for this curve, which we don't know. I mean, I just drew it randomly. But the point of knowing that there's like a potential function tells you that really the work will only be the difference in the potential here minus the potential here. Okay? Before I forget, the reason why we put we're not putting any signs here, the physics convention for potential involves a minus sign in front of this formula. But the difference is that that way they are evaluating the potential at the initial position minus the potential at the final position, while we're doing it in the opposite way. So there's a difference in sign with what physicists typically do, but that doesn't matter too much. So the way in which you find potentials in general is that this vector field has three components, F1, F2, and F3. Right, along the I component, J component, K component. And the gradient of any scalar field is just partial with respect to X, partial with respect to Y, and partial with respect to Z. And so in particular, this gives you a system of equations, and this is how we'll find the potential, which is that the first derivative of V with respect to X should be F1. The second derivative of V the derivative of V with respect to X should be F1. The derivative of V with respect to Y should be F2. And the derivative of V with respect to Z equals F3. And in general, this is what you always need to do for. So you must solve this system every single time you want to find a potential function. In our particular case, in this special case, F1 happens to be X plus Y squared. F2 happens to be 2xy plus 3y cubed. Plus 3y squared. And F3 happens to be 1 because that's what is multiplying the third component K. Okay, so that gives you a system of equations that you need to solve in order to find V. And this is maybe a bit similar to what you would have done in Calc 1, right? In Calc 1, if I had asked you to solve this equation, right, you would have said, well, maybe this is like df equals x squared dx, and then you integrate both sides, and you would get f equals x cubed over 3 plus a constant of integration, right? We're going to do the same. But now instead of integrating, I mean, the thing is like now you can not necessarily have to integrate against X. Maybe you can integrate against Y or Z. So you have to be a bit more careful, but the strategy is the same one. So in general, you can start with any of the three equations that you want let me start with the second equation. So the second equation says dv dy equals 2xy plus 3y squared. Okay? And so what I will do is like what I was just doing in this example. I multiply by dv on both sides and want to integrate that. Okay, and this behaves exactly as the integral that I was just doing. You should think of this as a partial indefinite integral if you want to put a name to this. So partial analogous to a partial derivative, right? Where only one of the variables is a variable and the others are held constant. Here, when you do like a partial integral with respect to y, which by the way, this is not a very standard notation, but it's convenient for now. When you do a partial integral with respect to y, only y is a function or a variable, and the other variables like x or z become constants. Okay, so that means that v will become, what's the integral with respect to y of this? Well, this is similar to what we have been doing with double or triple integrals. This gives you xy squared, right, plus 3y cubed, sorry, plus y cubed and here comes the main difference. So before with double integrals or triple integrals, we always had bounds here. So we never really bother about what the constant of integration should be. But now we do want to put a constant of integration, right? But so this should be a constant of integration, but remember that in the eyes of this integral, x and z are constants. So really this function can depend on x and z. So it's not really like a constant, it's a function because x, z are constants, or were treated as constants. And so the point is, why does this work? Because this satisfies, anything of this form satisfies the property that the partial derivative with respect to y gives you 2xy plus 3y squared. Right? Because if you take the partial derivative with respect to y, this gives you 2xy, this gives you 3y squared, and anything here, any mass that you have on x and z also gives you 0, right? That goes away. So a regular constant would have been fine, but also a more general constant or function that depends on x and z is something that can go here. And you need this flexibility because otherwise you could not make this system work. And so now that what this means is that we know that the potential function, whatever it is, must have this particular form. And so what you need to do is substitute it back into the other equations. So now substituting 1 and 2. Sorry, we already used equation 2, so let's substitute this v into these two other equations and see what we get. So v with respect to x is now y squared, this goes away, and now the partial derivative of c with respect to x, and this has to be x plus y squared. So this is the new equation 1. And new equation 3 is the derivative of v with respect to c. The derivative of v with respect to c, well, this goes away, this goes away. You only get partial of c with respect to z, if you prefer, so that they are more distinguishable. That's just one. So the reason why we have to put a function here and not just like a number is that if you had written a number here, this would have given you 0. So you would have obtained that 0 equals 1, which is not correct. So you need to allow yourself some flexibility here in order to capture the actual potential. And so let's solve this system. Again, you can start with 3. If you start with 3, then you're saying that the integral of z equals 1 with c. So you're integrating with respect to z. And so again, the left hand side just gives you z, and this gives you z plus a constant, right? But the constant, again, what was treated as a constant when you do this partial integral? Well, this was in principle a function of x and z. So x was still being considered a constant. So really the constant of integration here can be a function of, let me just put it like this, can be a function of x. Okay? So notice that this function in principle depends on both z and x. So let me just write it like this. So now you have new information about b, because now we know more about this funny function. We know that it must take this particular form. So what that informs us is that b, which depends on x, y, z in principle, is of the form x y squared plus y cubed plus z of xz, which is plus z plus z of x. Okay? So the point is that you start with one of the equations, integrate, get a function, then substitute it into the other equations, integrate again, get a new function, and then you finally apply it to the last equation that you haven't used. And so which equation haven't we used? Well, we haven't used equation 1. So equation 1 said that y squared plus the partial of z with respect to x. But the partial of z with respect to x, well, this one goes away, and you just get dc dx. And that has to be x plus y squared. And notice that the y squares cancel, and then you get a system that dz dx equals x, and so z of x equals x squared over 2, and now this is a plus a constant, and this is really a natural number, so let me just call it a for constant. Okay, and so again, now this tells you once you found more information about this function, you upgrade it and put it back into this formula. And so the general formula of the potential is that v of x, y, z equals xy squared plus y cubed plus z or plus z plus x squared over 2 plus a. And here a is an arbitrary number, arbitrary constant. So really, well, first of all, this tells you that potentials are not uniquely specified. They're really specified up to a constant. That's always the case. And let's just check that it satisfies the main feature that we were interested in. Notice that the gradient of this potential, what is it? Is y squared plus x 2xy plus 3y squared and 1. And that's precisely the vector field we had started with, if I'm not mistaken. And yeah, that's correct. Okay, so this is precisely a potential for F because like its gradient gave you the vector field. And so in general, to find potentials, you always have to do something like this. You start integrating with respect to some of the variables until you can simplify things out. And so now regarding to the last question in this example, so we're taking the particle from point P, which is 1, 1, 1, to point Q, which is 2. I think, I don't remember if I had written 2, 2, 2 or 3, 3, 3, but it doesn't matter too much. The point of this work is that the work will just be the potential at Q minus the potential at P. So no longer, so the idea is that no integral is needed. And so let's evaluate this out. So potential at Q minus potential at P, that's the potential at 2, 2, 2 minus the potential at 1, 1, 1. So at 2, 2, 2, well, this is 2 times 4, that's 8, plus 8, plus 2, plus 2, plus 8, minus, what do you get at 1, 1, 1? At 1, 1, 1, you get 1, 1, 1, 1 half, plus 8. So notice that the point is that the a's cancel. So you get 16 plus 4, that's 20, and then minus 3, minus 1 half. So you get 17 minus 1 half, which is 33 over 2. But the idea is that this did not require, you could skip doing the integration. That's the main point here. So in general, the takeaway of this example is that potentials are specified up to a constant. For actual computations of work, only the difference in potential matters, so the constants go away always. And in general, in order to find a potential, you need to solve a system of equations which requires you doing partial integrals. Now, again, next time I'll start telling you a little bit about how do we know that a vector field emits a potential function, but that's a very deep question and will require some of the remaining main theorems of this class.